Okay, welcome to class 2 of ETCS5200, Artificial Intelligence and Machine Learning 1. And today's class is thinking about artificial intelligence. Last class we went over kind of the course as an overview, went over some of the syllabus stuff. Today we're actually going to get into some of the actual material. And specifically, we're going to dig into some of the kind of conceptual or abstract things about intelligence itself. So here's an overview of what we're going to do. Like, I want you to think about, how do you think about artificial intelligence? What is intelligence? What do we mean when we talk about artificial intelligence? And what we'll find out is there's a lot of different ways of thinking about it and talking about that. So we're going to talk about the competing definitions of those things. And so the other part of this, and there's Loki, I mentioned him. He's back there making noises. But anyway, we're also going to talk about strong AI versus weak AI. And then we're going to look at the breadth and depth of the field. It really is a really large field. A lot of people don't realize that, especially recently. AI to everybody's large language models, and that's it. It's actually well beyond that, and it has been for quite some time. And then it says some examples on here. We'll probably hold off on the examples until a later lecture, because we do have quite a few slides I want to get to today. So probably won't get to the examples today. We'll probably do that next lecture. Now, getting a little further into this, first thing, what is it when we do? What do you think of, or when you think of AI? And now, there's kind of, when I talk to people, unless they are already computer scientists and they're already in the AI space, a lot of them, you say AI, a lot of people think of something like this. And so kind of the sci-fi version of what people think of when they think of AI. So we've got like Terminator robot there. We've got kind of GLaDOS from the Portal series over here in the bottom left. We've got R2D2 and C3PO. We've got Data and Lore. We've got Wally. We've got HAL 9000. We've got Agent Smith. And so these are all kind of sci-fi representations of what people would think of as AI, or what people have imagined AI to be in the future. Or one thing to note about this, though, is notice that a lot of this, there's a lot of evil AI going on here, like the Terminator robots, the GLaDOS and the Portal series video games, lore in Star Trek, R2D2 and C3PO, mostly good. C3PO, a little bit weak personality, but mostly good. Wally trying to do good, and then HAL 9000. I don't know if evil is the right word, but definitely flawed in how it was programmed. But a lot of people will think of AI as one of these kinds of things, with a lot of kind of evil, uncontrollable kind of aspects to it going on there. Now, also a lot of people now, due to the success of large language models, will think of AI as one of these things, like ChatGPT or Google Gemini or Copilot or Claude or Meta or XAI. Those large language model companies, that has become synonymous recently with AI because they're now so widely used. And again, that's not all AI is, but again, ChatGPT, is that good or evil? You can make arguments either way. Same thing with Gemini. Is it good or evil? Copilot, good or evil? Claude, good or evil? Meta, I just put evil on that one, and same thing with XAI. But all of these are really just tools, and it depends what you do with them more than anything else, but there is a potential there for them to be used for truly terrible purposes, but there's also potential there for them to do good things and help things. I think it remains to be seen how this will play out. But again, these are kinds of the two things that people tend to think of when we talk about AI as either sci-fi, kind of evil robot kinds of things, or large language models that you ask questions to or give prompts and they chat with you and give you answers to help you with things. Now, one of the things, though, that may be happening is it might be that all those Chat GPT, Gemini, Copilot XI, maybe that's leading us towards that future with those, that dystopian future of evil AI robots that want to do away with humanity. Again, that remains to be seen. There are right now not a lot of guardrails on that, so there's a little bit of maybe playing fast and loose with the future of humanity by some of these companies just rushing toward making potentially superhuman intelligence. Again, remains to be seen. Hopefully that's not what's happening. But it wouldn't be the first time that we made, as humans, technology that turned out to have the potential for horrible consequences for humanity. Now, before we go down that dystopian sci-fi road, though, and like talk doom and gloom and worry about what it is we're doing here, I want to take a step back, maybe wrap our minds around some definitions, or at least do some thinking around those definitions. So specifically, what is intelligence itself? So we're talking about artificial intelligence. What is intelligence? And then once we kind of think about that, what does it mean for that to be artificial? What is artificial intelligence? And there's obviously a joke that could be made there. That's low hanging fruit. I'll leave that. I'll probably make it later. But if we think about that, what is intelligence and or artificial intelligence? And I'm going to just pause here again and let you guys kind of think about that for a second. And then kind of just think of what you would consider intelligence or artificial intelligence, how you would define those terms. So let's go ahead and just pause there for a second. And if you need to, pause the video, maybe write down some ideas. I would like you to actually pause the video here and write down some ideas like what to you does the word intelligence mean? And what to you does artificial intelligence mean? Is it, and try to avoid that kind of sci-fi dystopian robot, and try to avoid using things like ChatGPT. Try to use something a little more generalized as your definition, or a little more abstract, a little more broad as your definition for those two things. So I'll give you a couple minutes here. Okay, so seriously, pause, write down at least 3 kind of ideas or definitions for each of these 2 terms. Don't just pretend you did and then watch the video, rest of the video. I'll give it another minute here. Okay, so let's continue on now. All right, now let's see if what you came up with was anything like these kinds of definitions. So now I'm going to go through and kind of have these come up, and we'll see if you have anything like any of these. So intelligence or artificial intelligence is that things that act rationally. And act rationally, I mean, that's open for interpretation as well. What does rationally mean? But maybe you had something like that, or maybe things that think rationally. In other words, something that just acts rationally, follows a sequence of like rational, like do A and then B and then C, that might act rationally but not really think in order to carry out those actions. So notice the use of the word think there along with rationally. Or maybe things that act like humans, things that act like we do. Like kind of like Data in Star Trek. Data looks human, mostly acts human. Sense of humor is a little off in that fictional interpretation of Data as a AI entity, but is that what intelligence is? Is things that act like us? Or is it things that think like us? Things that think like humans think? Does it have to like think or act like we do think or act to be intelligent? Maybe you had a definition of something like that. Or maybe things that produce a novel solution to a problem. In other words, they're presented with a problem and they come up with a new way to do it, that they're not pre-programmed. In other words, they're not pre-programmed. They're not hard-coded to solve it in a way. They come up with the solution on their own. Maybe things that I kind of identify patterns automatically. They look at data and they extract patterns from that data in an automatic way without having to be told how to find those patterns. Or maybe things that adapt and learn. In other words, they're put in a situation and they change their behavior based on the situation they're in. They, over time, as their input stimuli change, they change and adapt to that in a different way. Or maybe things that do things that are difficult for us to do. Like, here's a problem that's hard for humans to do. Here's a machine that can solve that. Does that make that intelligent? So, for example, I might think it's really difficult for me to figure out how to do some sort of particular math problem, but I take it to my friend who's a really talented mathematician, and she looks at the problem and says, "Oh, I know how to do that." Then my thought is, "You're really smart. You know how to do something that's difficult for me, and you seem to make it easy." That might be my definition of what intelligence means. You can do something that I have a hard time doing. Now, if you had any of those kinds of things or something along those lines, then that's probably pretty typical for what people tend to think of with intelligence. So we're going to kind of drill down into some of these a little bit further. And maybe you had something totally different from this. If you did have something totally different, I want you to go to the chat. Or even if you didn't have something totally different, and kind of go to the chat and put in kind of your thoughts on what you had or what you defined intelligence as, and chat to some of the other people in the course on that. Now, let's drill down into some of these. So let's start off with the kind of things that act rationally. Let's start off with that top one. Now, things that act rationally, which is what we'd call kind of rational agent approach. And what that is, the idea there is that we want to create these agents or entities, we can think of them as, and they perform these desired tasks really well. And possibly they do that autonomously. Possibly they adapt to change. Maybe that's a requirement. Maybe it's not. I'll let you think about whether that's a requirement or not. And maybe they develop a goal and then they pursue that goal. Like they have some task that they want to accomplish. They recognize that. And then they develop a goal to accomplish that task and then pursue accomplishing it in some way. Now, maybe we would also think that they want to achieve some best outcome or best expected outcome, almost like optimizing as they go. In other words, finding a solution just through randomly guessing and checking, we wouldn't necessarily think as intelligent or rational. We want something where it kind of finds a good solution for something, or maybe even a best solution for something. Now, pausing there for a second, are there any issues or weaknesses with that rational agent approach? Is it missing anything? Like the achieving that best or best expected outcome, or uh, performing a task really well? Uh, are there any issues with that kind of approach to thinking about intelligence or artificial intelligence? So I'll pause for a second, let you consider that, and then we'll see what issues that I came up with in the slides when I was making this and see if they match what you maybe thought through. Okay, now here's some issues that I came up with. Well, first off, if we're going to have this achieving the best or best expected outcome, how would we know that? How do we know what the best or best expected outcome is? And in other words, we would already have to know what the best expected outcome is beforehand. And then if we knew that, then why would we need this agent or this system to do that for us? And then the second part of this is, notice up there at the top, it says it performs a desired task or tasks really well. Is performing some narrow task or set of tasks really well all there is to intelligence? So, for example, if we have this well-defined set of tasks, is that, and we can perform that really well, even if we have to adapt to perform that task well, does that make us intelligent? Does that define something that's intelligent? And I'm not going to say yes or no here. I'm going to leave it more open-ended than that, but I think it's worth considering. Does something that does a task really well, even if it has to adapt to some sort of change in order to do that task, does that make it intelligent? And if it is adapting and solving that problem, how do we know if it's doing a good job of it? How do we know, unless we already know what the solution is, how do we gauge whether it's doing that, solving that rationally or intelligently, or in a terrible way? Or maybe if it doesn't find a solution, how do we know if maybe the solution exists, but it just didn't find it? There's a lot of kind of issues around this kind of rational agent approach here that are worth thinking through. All right, so let's look at another one. Let's look at things that think rationally. And this is a lot of times what we'd call the laws of thought approach, where the idea here is that rather than focusing on what, let's go back a second. This one knows it's like focusing on pursuing a goal and what it's doing. We're focusing on this outcome of what's happening. But over here, we're more focused on the kind of internal states. We're developing and implementing something that is perceiving through inputs, and then it has this internal reasoning that's happening, and then it's acting based on that. So it is still acting, but we're focusing more on the thoughts and the progression of those thoughts that are happening internally, that are leading from the input through the reason to the action, rather than just the actions themselves. So in order to do this, that means we have to have somehow inside the system itself implement those laws of rationality and thought. In other words, when you think through some rational solution, says, okay, if I don't, this maybe isn't super rational, but for example, if I say, if I poke myself in the eye with this pencil that's on the table, that's going to hurt, and so I should not do that. There's a sequence of chain of thoughts there based on past experience, based on perceptions, based on a reasoning chain. If I do this, then this is going to happen, and I don't want that to happen. And so I'm not going to do that. Or also actions. If I do this, then I know that will cause this, which will cause this, and that will lead to this outcome that I want. And so that chain of rational thought processes from perception through the sequence of reasoning, the chain of reason, through eventual action, is kind of what we're doing is we're implementing this conceptual process of mind that we as humans feel like that we're using when we're making our decisions. Now, are there any issues with that kind of approach? Like, what would you think would be potential issues with that? So let's pause there for a second. I'll let you think through. And then we'll flesh that out a little more and look at some of the issues. And again, remember here we're focused on that internal state leading to from perception to action, a little more than just the action or just the outcome that we had before. Okay, so in thinking about just that internal sequence and thought processes, here's some issues that we might consider with that. That how do we, if we're going through this kind of formal sequence of reason, that like I just mentioned, that I perceive this and that makes me think this, which leads me to think this, which leads me to think this. That means that we have to have some way of taking the knowledge we have and putting it into formalized statements of logic or a chain of reasoning like that. And as humans, a lot of times I don't think if you try to figure out like, why did I make that decision? We can't always pin down why we did what we did, or we can't always pin down. And maybe that's because we're making irrational choices. Maybe it's because we're making a rational choice, but we can't tell why we're making that rational choice. But the idea here is that becomes especially difficult when we don't have full knowledge, or we're having to make more fuzzy sorts of guesses that are I think that this will cause us, or I feel like this is the best approach. Let's try that experiment with that. And so when you're dealing with kind of intuition or feelings, or that's still intelligence guiding that in some way, but it might, or probability maybe even guiding that, but it's something that's harder to pin down as a formal sequence of logic, like this causes this, causes this, causes this, so I'm going to take this action to get the outcome I want. It's a lot more difficult when you have this may cause this or this or this or this, and there's, I don't know, a dozen or even hundreds of possible outcomes that all lead to hundreds of other possible outcomes. And when you don't even know the probabilities of each of those, it gets a lot harder to have this laws of thought when you don't know what the rules are, or what the laws or what the probabilities are. So that inferences that are correct kind of require complete, that are provably correct, require total knowledge of a system along with the rules in a formal way to process that and get us from perception to through chain of reason to action. And that just isn't the case in a lot of types of information. And so that other part of that is it really intelligence if we just have this formal set of logical rules and we just encode those in some sort of almost like a database, and we just apply them? Does that intelligence? In other words, if it's almost like a big if else statement. If this causes this, then that leads to this, then that leads to this, then that leads to this. And so I'm going to take this action because that gets me to the goal. It's more like a searching through a space than it is a problem space than it is intelligence. But maybe that's what intelligence is. It's really hard to wrap our mind around that. Is it intelligence to just search through a chain of reasoning and come up with an action? And one example here might be, like, for example, chess. You might say, if I move my pawn here, they will do this, and then I can do this, and then they will move their knight there, and I'll take that with my bishop, and then they can do this, which will fork my rook and my queen, and then I'll lose a piece, so I'm not going to do that. Notice how that's a formal progression of logic based on perception and leading to a decision and a kind of action, whether to make the move or not, or make a different move. Is that really intelligence? Maybe it's partially intelligence, but that's something to ponder as well. Now, moving on from there, let's move into more of that ones where maybe you've thought of things that act like us or things that behave like us, the human side of things. So things that act like humans. And this is more of that, what we'd call the kind of Turing test approach. The Turing test approach is like where we're creating machines that behave like we do, they respond like we do, because we, as humans, we think we're intelligent. And so if we make something that acts like us, we've made intelligence. And so we want to create machines that perform functions that require intelligence when performed by people. So if we can make machines that act like people, then we've solved the problem. So if we can create systems that are indistinguishable from people, then we've created things that are intelligent. Now, is creating something that acts like a human or is even indistinguishable when we interact with it from a human, is that intelligence? So what issues do you find with that? So let me pause there again for a minute and let you ponder that, and then we'll discuss this one. We'll go through some issues with this one as well. So can you think of any kind of flaws or any issues with something that acts like a human and defining that as intelligent? So for example, I could be like a AI generated talking head delivering this content that you might think is human, looks human, acts human, but if I just trick you, does that make it intelligent? All right, let's look at some issues. Now, issues with this, first part of this is humans, as I'm sure everybody in here watching this knows, aren't always rational or optimal in our approaches to things. In fact, we're a lot of times completely irrational in our choices. Our choices are driven by emotion or irrational things. We can get tricked easily. We have behavioral limitations and intellectual limitations like biases and kind of a lot of times that can be taken advantage of or used against us. And so I don't think there's a person who's ever existed that acts completely rationally. And so making a AI entity that models that might not be what makes something intelligent. In fact, something intelligent might avoid the irrational behavior of humans. It might do something that's different. And also, putting this in that third bullet point there, trying to make something that pretends to be human or acts human is kind of like you don't have automotive engineers trying to create mechanical systems that behave like horses that can fool other horses. In other words, hey, what's the best way to make a vehicle? Well, for years, humans rode horses, so let's make a horse contraption that can trick another horse into thinking that thing's a horse. So why would we want to make an AI entity that tries to trick humans into believing that the AI entity is itself a human? That doesn't necessarily make it intelligent any more than making a horse vehicle that can trick a horse and saying that's actually a horse. And so the idea here is that mimicking a human might be just a good mimic of a human. It might trick people into thinking it's a human, but is it intelligent? Or is it just a really good mimic? Is it really just a good like trick? And so is a convincing almost like game that you play where you trick somebody into thinking, hey, that's plausibly human. Does that really mean it's intelligent? I don't know that it does. So, for example, I said that earlier. You could imagine the case where you have something that just looks a lot like uh, a human, acts a lot like a human. It could have just a database of all of these conversations that have happened in the past. And when you talk to it, it responds in the way that makes sense. You're like, oh, that sounds just like a person would respond. But does that mean it's really thinking? Does that mean it's really pondering things and coming up with answers to things? And I don't know. It seems to me like it doesn't. It might, but it doesn't necessarily mean that. Now, let's go on to the next one. And it's like, instead of acting like a human, again, this is kind of just looking at it from the outside. Like, it looks human, must be smart. Let's move on to the one that's that cognitive model approach that we talked about earlier, where rather than acting human, it thinks like a human. So here we are with kind of more of the, can we create something that perceives and processes and thinks like people? In other words, now instead of focusing on what it looks like on the outside or acts like on the outside, we're focusing on how it does things internally. In other words, if we can make something that looks at the world the way humans look at the world, processes the data in the world the way humans process data in the world, and then thinks about the world the way we think about the world, then we have created something that's truly intelligent. And the idea here is that that would allow us to even automate things like human type things like problem solving, decision making, learning by modeling the way humans do it. We could have a machine that kind of models all of those internal processes that lead us to do what we do. So we're kind of building these models of perception, how we look at the world, but also cognition, how we think about the world. And then ultimately that leads us to how those systems would react to the world. So this is kind of the concept of, notice on that last bullet point there, creating machines with human minds, that they are like us internally, not just a mimic that looks and pretends to be like us, that they think and react and perceive like us. Now, let's pause there for a second and let you think through if there are any issues with this sort of model of intelligence and artificial intelligence. So this is the cognitive model, things that think like we do. And presumably they think like us, they would also act like us. So this is a little bit stronger than the Turing machine one that we had back here with things that act like humans. This is they think like us, so therefore they will also act like us. And if you hear noise, there's construction going on, so apologies. Okay, so here's some issues that we would consider with that one. First issue, and this is a really one of the big ones. We don't really know how humans think, which is weird because that's us. We don't know how we ourselves work. So creating a system that works in the same way that we do when we don't know how we work is a lot more difficult than it might first seem. You might think, for example, if I ask you a question about something in your daily life, you might feel like you can pin down your thought processes. Here's how I got to that thought process. Like I might ask you, like, for example, hey, what's your class schedule like tomorrow? And you would access your memories and your database of stuff that you remembered and try to come up with this response. But pinning down at the exact level of how you came up with thinking through that and coming up with that, it's not as easy as it sounds. It's like we are our brains themselves are kind of like this black box to us in a lot of ways. We're making progress at parts of that. We know regions of the brain do certain things. We know kind of how neurological systems work, and we're making systems that kind of approximate that. But we don't have anything to the scale or capability at the neurological level that humans have. And when we've tried to build things at that level or that scale, they tend to not work. So there's some stuff where there's knowledge we're missing. We're getting closer, but we don't know that. And even if we made a neural system that was able to do that, that's not understanding the model of cognition. That's not understanding the process. That's just making a thing that kind of copies the machinery, not understanding the process. So understanding that cognition process is a lot more difficult than you might think. It sounds easy to say, let's just make something that thinks like we do and then it'll be intelligent. Well, we don't know how we work. So that's hard to do. That's kind of like saying, oh, you want a magic wand that can do real magic? Well, just make a copy of the magic wand that does magic. Well, if you don't know how it works, you can't make a copy of it. Now, also, it's also still important to note, and I mentioned this earlier, that human cognition itself is maybe non-optimal, has baked-in limitations that might be counterproductive to duplicate. Like we have confirmation bias and other biases, and we make shortcuts and we make poor decisions all the time where we rush to judgment, and that's why there's so many logical fallacies that we fall prey to when we're that's why propaganda works on us, is we're not logical a lot of times. We make poor choices. So human-like cognition might not be optimal or even desired. Do we really want AI entities that make poor choices like humans do? Do we really want AI entities that get emotional and make emotional decisions? And so that kind of human thinking is really, when it boils down to it, it's all of your thought processes are driven by emotion, whether you like to believe that or not. Even if your emotion is an emotion that is an attachment to wanting to be logical and reasonable, that's still an emotion that's driving that. And that's why science is such a worthwhile endeavor, is that it created a process that can kind of cut through the human failings of wanting something to be true and therefore believing it by having things like control groups and double-blind studies and reproducing results with one group and another from one experiment with another one. And all of those, the scientific method, all of that is in place to get around our kind of human limitations that are based on emotions. And so that human way of thinking, if we copy that, we're likely to also copy the bad parts of it, the failings of it. And so it might be bad for us to do that. So that cognitive model, let's just copy what humans do, maybe not a good idea. Even if we knew how to do it, maybe it would lead to systems that make poor choices. Like, do you want your AI super intelligence to get enraged and then, like a angry toddler, start, I don't know, launching nuclear missiles at humans to get even with us because it got mad because somebody called it, I don't know, Sparky or something like that. And so, again, cognitive model could work if we understood how humans thinking worked, but maybe not a good idea even if we could do it. So that takes us to this diagram here that's kind of like these dimensions of thinking about intelligence. And along the x-axis, we kind of have on the one side human-like behavior. So that's more of that Turing machine approach all the way on the left. Does it act like a human? And on the right, we have rational behavior. Does it follow a set of logic and reason when it makes its decisions? And notice those are kind of non-accidentally opposed to each other. Humans don't always make good rational choices. And rational behavior, sometimes rational choices run contrary to human choices. And then in the y-axis, thinking is at the top. That's the internal processes of what is causing some thing to happen. And then at the bottom is acting. That's the actual result. And so if you put those into the 4 categories, you'll notice that something that acts like a human-like behavior, and acting like a human, that's kind of that Turing test in that bottom left quadrant there. In other words, we don't care how it works. We don't care how it thinks. We don't care if it's rational. We just care, does it act like a human? If it does that, then we pretend it's intelligent because it tricked us into thinking it's a human because it acts like one. Now, if we move up to that top, that cognitive model approach, that's something that thinks in a human-like way. So we have the human-like behavior and the thinking. So the internal processes are human-like. But then if we move to the other, so that's the top left quadrant, and then the top right quadrant, we have things that think, but they're rational in how they think. That's more of the laws of thought and logic, where if you have all these formal laws of logic laid out, if A, then B, then C, so, and then not D, then you go through this progression and you know what your answer is for how to behave or how to act. Notice that's all about the thinking and all about being rational. But that's about the process of how we get there. But then the bottom one is acting and then rational. That's more that rational agent approach, where we don't care how it got to that solution, just that it did it. And so it could be something like a giant database of actions. Hey, when this happened last time, let's do that same thing again. That could be copying something that itself is intelligent in a statistical or a probabilistic way. But again, is that intelligent? And so notice there's kind of these different ways of thinking about that come out of the that each of those viewpoints. Now, there are some other ways of thinking about this as well, and we mentioned these earlier. That these were on your the list earlier, where we talked about things that produce novel solutions to problems. In other words, a lot of times we think of, if something can invent something that nobody else has invented before, it hasn't been invented before, it has to be intelligent, right? But it turns out that there are systems like genetic algorithms, for example. And what genetic algorithms are is, actually, this would have been fun to play with, but we don't have time for this semester. Genetic algorithms allow us to kind of copy the way natural selection works in the natural world, but do that digitally. In other words, have a population of solutions to some problem, have them mutate and create a next generation. The ones that do better at solving the problem survive and reproduce with the other ones, kind of combine traits with other ones. And then over many generations, we get something that now solves this problem in a way that maybe we didn't even think of, in a way that is better than anything we could have thought of ourselves. And interestingly, that can happen just through kind of random mutation and selection pressures. And so it can come up with a novel solution. For example, there are patents in the US Patent Office that were for machines that were invented through genetic algorithms. In other words, you think of, a patent is like a really intelligence driven process to dream up an invention that no one has dreamed up before, create all of the details for how that invention works, and then get a patent on that. But genetic algorithms can do that with just the process of randomness and selection pressures and kind of mutating these things over generations until you get this thing that now solves this problem in a way that you didn't think of before. And you can see that in nature as well. You see, you have some sort of bacteria and you put it under these different conditions, and then it changes its genetic code to now be, antibiotic resistant or uses a different food source. And that's why we get the whole tree of life with all these different solutions to different survival biotas in the natural world. And there's also kind of novelty searches where you search through a search space and look for new solutions to things, like drug companies do things like that. Find new ways of combining all these molecules together to create a thing that now looks chemically like it'll solve or be a new antibiotic or a new chemistry for this. So it's a new solution that's never existed before, but it came about through a search process, not through thinking or reasoning. Or Monte Carlo methods. Monte Carlo methods are kind of statistical based methods where you kind of, it's almost like throwing darts at a dartboard, and then you kind of take the ones that came closest to what your solution was and you throw more around that one. And then the ones that did better, you throw ones around that one. So there are Monte Carlo processes that you can get to new and novel solutions to problems, or optimize a solution to a problem. That doesn't necessarily, but none of these, if we think about them, have much in the way of logic or reason underpinning them. They're just kind of, you set them loose and they do a thing and they produce a solution. Not a lot in the way of logic or reason or what we would normally consider high-level thought. So the issues here is with those, we kind of just talked through these, but that idea of thinking of a novel solution of a complex design as a hallmark of intelligence, well, it could be. A novel solution could also be achieved just using computational brute force or randomness combined with genetic selection pressures, or it could be randomness combined with some sort of other guiding metric where we're looking for specific traits in those things, and then not necessarily anything that's thinking or reasoning to get where it's going. Again, think of like a chess program that just looks into the future, brute force. It's not thinking about anything. It's just saying, what if I do this, this happens. If I do this, this happens. So it's not really, there's not really a thought process there. It's more of just a thing that it's searching through a bunch of search space to find a solution. Now, we also mentioned early on things that identify patterns, including automatically identifying patterns. So statistical or probabilistic approaches like principal component analysis. In other words, finding the most sensitive component to something, or data analytics, or algorithms that find and extract patterns from things. There's a whole bunch of those kinds of pattern extraction algorithms. And the issues with those is that, is an algorithm that finds a pattern really intelligence, or just some narrow implementation of some like single dimension or single indicator of intelligence? So in other words, writing a program that says, oh, I found a pattern and here it is, well, it might take a human intelligence to look at all that data and then go have an aha moment, look at that. If you just turn an algorithm loose on it, really that comes back down to like these ones back here. It's just a search for something that might not take intelligence at all. It might just take computation. So is identifying a pattern, or even like a large language model, reproducing a pattern in a plausible way, is that really the same as true understanding, or a thought process that is logically progressing through a chain of rationality to get to that pattern? So is reproducing something, this kind of comes back to the Turing model, is something that's reproducing something or copying something necessarily intelligent just because it has some semblance to things that are intelligent? And then the kind of last few of these before we move on and that's things that adapt and learn. In other words, things that change their behavior based on the situation they're in. So certainly that is something that if something that's not intelligent will do the same thing over and over again. Like um, actually just yesterday I had a bird trapped in my third floor of my building here, and it kept flying into the window over and over and over again. And I thought to myself, that was a starling. I thought that starling is really stupid because it thinks that it's going to get through that glass window, and it has not. It's done the same thing 10 times in a row, and it keeps running into the glass every time. And so it would be more intelligent if it adapted and learned from that and said, oh, I ran into that window. Maybe I'll try a different one, or maybe I'll try the bottom part of the window instead of the top. And so I eventually did get it to go out of the window by covering up the top where it was running into and opening the bottom. And then it finally flew out and was safe. But adaptation and learning, in other words, modifying your behavior to optimize going forward or to do something different going forward, that is clearly one of the things that we consider a hallmark of intelligence. And there are systems that are like either supervised learning, where it does something and then you correct it, you teach it, or it's unsupervised, where it kind of self-corrects and learns on its own. There's also reinforcement learning systems and kind of online or continuing learning systems that are continually kind of course correcting. And there's some issues with those too, though. Those often devolve into that kind of pattern learning with optimization that we saw in the previous slide. And again, optimization of results, does that necessarily require understanding? Also, if those systems don't have a mental state, in other words, they're just this optimization algorithm that's like changing and modifying its behavior. But if it's not cognitively self-pondering why it's making those changes or why it's updating those things, in other words, it doesn't have a sense of self, is that really intelligence? Or can you even have intelligence without consciousness? You can have something that looks or behaves sort of like intelligence, but does that make it intelligent? And those systems, one way to say it is without a sense of self, they kind of lack intentionality. In other words, you give them the goal of what they're supposed to optimize towards, and they just do what they do. Kind of like they might optimize, they might change their behavior to reach a better version of that goal, or that reach that goal more easily. But are they intentionally doing that themselves? And that also begs the question that, how do we know we're actually intelligent and not just this optimized, self-optimized thing? That how do we even know that we have a sense of self? All right, so now that we've gone through those, let's go into the actual dictionary definition of intelligence. And this lecture's going on, we're at like 50 some minutes right now, so I don't want to spend too much time on all these additional slides. But what is intelligence and what is artificial intelligence? So here's the dictionary definition of intelligence. This is the number one definition anyway on dictionary.com. And it is the ability to acquire and apply knowledge and skills. Now, which one of those four models does that seem to fit best with? So acquire and apply knowledge and skills. I'll leave that as an open question for right now. But the important part here is it's not exactly clear what we mean. So in other words, acquiring knowledge, that could just be storing something in a database, and applying that knowledge, that could be storing something or using the thing in the database in some way. And then skills, what does that mean? That just means taking an action maybe based on what you've stored. So you could very easily classify a lot of things as intelligent that we would not consider to be intelligent. Like, for example, you could say, a Rolodex or your cell phone that remembers the caller history. That's intelligent because does it acquire knowledge? Yeah, when people call, it remembers that. Can it apply that? Yeah, you can call people back after they call because it remembered who you called. And so that's kind of a skill. But is that a thing? Is your call history in your cell phone intelligent? We wouldn't think so, but it kind of fits this definition. So that's not exactly a clear definition. So let's move on to artificial intelligence. So here's artificial intelligence. The definition for that is, again, this is from the uh, dictionary.com. And here's the pronunciation guide here. Artificial intelligence. All right. Anyway, the definition here is the theory and development of computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. Now, notice that this definition, well, two things about it. The first thing is they're using a human-centric model here. They're saying tasks that normally require human intelligence. So that's kind of the human things that act human model. They don't say anything about it thinking like it. It just talks about tasks, so things that behave like a human. And then they give a list of things like visual perception, speech recognition, decision making, and translation between languages. We have software that does all of those in some form or another. And those are parts of the AI subfield, so it does a pretty good job of that. But does that really mean those things are intelligent? In other words, does a algorithm that takes speech and turns it into text, is that intelligent? Or is it just a really clever algorithm? Or is an algorithm that translates something from one language to another language, is that really intelligent? Or is it just another clever algorithm that a human wrote? And the other problem I have with this definition is we're trying to define artificial intelligence, and notice that it has the word intelligence in it. And so it doesn't really help us pin down what intelligence is. We're just saying artificial intelligence is something that kind of normally acquires intelligence. It's a computer system that normally requires human intelligence, which isn't a bad definition for artificial intelligence, but doesn't get us any closer to having a good understanding of what intelligence actually is. Now, let's talk about weak AI versus narrow AI, or versus strong AI. So weak AI or narrow AI, this is the AI systems that are designed to perform a specific task or a narrow set of tasks, like we just mentioned, like speech recognition or even language translation. It's a system that's designed to do a thing, and it does that thing. Now, in other words, it kind of mimics intelligence without necessarily understanding anything or having consciousness. This is what most people think all AI systems are right now. In other words, these are all limited. They can't generalize beyond a limited set of whatever domain they were designed. In other words, your speech recognition algorithm that's in your Alexa device is not truly thinking. It recognizes the speech using one algorithm. It sends the thing to the Amazon servers, which field the query with a different algorithm, and it gives it back, and then it uses a speech synthesis algorithm to produce the thing. Those are all individually things that humans would normally have to do. So they all fall into this definition of artificial intelligence we had back here. But it's not really, it's mimicking what a human would do to answer a question without having consciousness or understanding. Most people would consider that. So that's weak AI, also called narrow AI. Now, strong AI, also called general AI or AGI, that's a theoretical form of AI that actually possesses general intelligence. And AGI is artificial general intelligence. I just mentioned AGI, but that's something that's comparable to human cognition or beyond it. And that is something that can truly understand, learn, apply knowledge across this wide range of tasks. It would be self-aware, conscious of itself, and have the ability to reason and plan just like a human, or even beyond the capability of what humans can do. Now, most people in the industry don't think we've reached this yet, although it's still the subject of debate. Some people think that some of the newer large language models actually are a form of intelligence, a form of general intelligence. In other words, their argument is once you get to a certain size, then the model has this emergent behavior where it becomes able to do things that only could be done if it is a general artificial intelligence. So we'll look at that more later. But right now, most researchers agree that we have not gotten to strong AI or AGI, artificial general intelligence, yet. Now, as far as the breadth of the field, and I'm not going to go through all of these, but if you want to look through these, is the AI field itself is huge in its breadth. That machine learning, natural language processing, cognitive computing, and neurosymbolic AI, computer vision, in other words, notice on this is a lot of stuff like machine learning, getting the computer to learn, computer vision, getting it to see and perceive, natural language processing, getting it to understand our language and speak back to us, robotics, getting it to move and plan and interact with things in the world, knowledge, representation, and reasoning, getting it to think through problems and come up with a plan to solve those. And that also goes into that planning and decision making that's below it. Speech and audio processing, getting it to listen to us and then speak back to us. And then generative AI is getting it to do creative sorts of things like create pictures or generate video, generate text. And then we also have kind of game AI, where either making the game adapt to us, change its tactics, or adding human elements to it with dialogue and making these really rich interactions where it's more like we're talking, rather than having pre-planned dialogue where the non-player characters always do the same things and react the same way. It's more like they're real entities we're interacting with. And then around that whole AI space, there's all these supporting domains as well that are not necessarily completely independent from AI, but also not necessarily exactly directly the technical side of AI as well, like data science and data engineering. So this is, how do you get the data and collect it and clean it up to feed it into these AI systems? Or how do you mine the data and perform data analytics to find those patterns in the data so that it can be either given to AI, or how can AI help with that? There's also human-centered AI. Part of that is going forward is becoming more important is explainable AI. In other words, when an AI entity gives you an answer to a question, how do we know that it's not hallucinating or lying to us? So explainable AI kind of tackles this approach of when it gives us an answer, having it so we can look back and audit and figure out why it gave us that answer. And that can be important. In other words, if you ask an engineering question, like, let's say we're designing an aircraft, and we say, what does the surface area of this wing surface need to be for this new aircraft design? It just gave us a number. And if we just relied on that, that could be really bad if it made a mistake. So instead, we need to say, give us this answer, but also tell us why this is the answer. And then we need to trust that what it gave that was explainable was why, or can be followed and is true. And so there's kind of a rabbits all the way down kind of thing with that. Who watches the Watchmen sort of situation there. But the idea there is there's a lot of that explainable AI stuff that is going to become increasingly important. There's also things with human-centered AI. Like how do you make AI systems fair and accountable and transparent? How do we make sure that there's no bias in our systems and that the AI is used ethically? There's a lot of things around that. And then over on the right-hand side, we have these AI systems and engineering. And those deal with, like, how do we make sure our AI systems are secure, that somebody's not poisoning uh, the minds of our AI, or um, how do we deal with the AI infrastructure itself, making the hardware capable of running our AI models? How do we deploy those models onto these uh, large scale systems and then have it scale uh, as we grow the amount of interactions we need to have with it? And so there's a lot of stuff that, and then there's a lot of theoretical foundational things as well, with like formal logic, with kind of computational learning theory, even cognition theory on the um, more the uh, psychological side of things, like understanding how humans learn can help us make machines that learn better. Um, so a lot of different things that are supporting domains related to AI. And then as far as areas where we can apply AI, again, pretty much everywhere. Healthcare, finance, security systems that automatically look for suspicious behavior. That could be computer security or physical security, entertainment, education, science, innovation, pretty much everything else. It has a. It's hard pressed to think of a. Humans have done a lot in our history on the planet, using our intelligence. So it's hard to imagine any place where AI can't provide some sort of application or have a role in um, that in some way. And so uh, all the way from something like farming and improving the yield of crops, all the way up to entertainment things like games and uh, personalized learning and virtual reality sorts of things, adaptive play system, all of that is a place where AI can take uh, hold. Now, this semester, all of that stuff we just saw on those previous three slides, the AI subject field is so broad and so deep that we don't have any hope of covering it all in one semester or two, which we have, or even 10 or 50 or ever, because the reason we can't ever cover it all is because the field is growing faster than any one person could ever learn about. In other words, it's exponential explosion of uh, new knowledge and new stuff. And so it's tough for us to. We'll do a good job getting a nice overview of a lot of these things, but we're not going to be able to be on the cutting edge with all of those different things all at the same time. So, what are we going to do if we can't cover all of it? Well, we're going to kind of get our feet wet, learn some really cool things about machine learning and AI. We're going to learn about some things related to that kind of transcend technology itself, about information and patterns and data in general, which all kind of underpin most of the AI systems that you see. We're going to learn things about language and text-based patterns that show up in language. That is something that uh, a lot of those systems rely on. And that's not just true when I say language. Doesn't mean just like English language or spoken language. There's patterns and language patterns in things like genetic codes and other things like that as well, or the patterns of the language of uh, things like whale vocalizations and bird vocalizations. So there's all kinds of things that when we say language, that it could be pattern based things. And then the we're also going to learn about how we can apply what we learn up there about information, patterns, data, and language to a lot of other fields. And I kind of just mentioned a few of these, like genetics. It's a code. It's a code that has patterns in it. Programming, like if you look at programming code, That's a language that you write code, and those patterns cause the computer to do things. And so biology itself, patterns of uh, growth and leaf structures and behavioral patterns, music, obviously patterns, speech, obviously patterns, and so forth. And we're going to spend time playing with this stuff, writing code that does this stuff, and it should end up being quite a bit of fun. So here's our semester plan. We're going to be doing assignments. We're going to be doing labs. There'll be some quizzes and some check-ins along the way too. But what we're going to do, excuse me, is we're going to be learning about a lot of data structures and algorithms and programming as they relate to machine learning and AI. And then we're going to use that to write some code from scratch, then develop things that learn and do things. And we're going to get there pretty quickly. And then we're going to read and process and extract patterns, and then we're going to have code that like creates patterns from the stuff that it learned. And then we're going to kind of, like we mentioned this in the last class, but we're going to kind of, toward the end, make a chatbot that learns from us talking to it. We can teach it things, and it's going to chat back with us about what we've taught it. Now, we're not going to use a large language model for this. We're going to do it in a more of a traditional probabilistic way this semester. We'll get into the neural systems next semester. So you're also going to be writing code. We're going to use Python. We'll review the stuff that we need to, but you're also going to learn some new things. You're going to use some modules and professional toolkits, but for the most part, I want to avoid black box solutions. I want to use things we understand. So you're going to learn things also that aren't just Python, that transcend the programming language. So mathematical concepts, data structures, algorithmic things, new problems that you haven't seen before. Now, a few final closing thoughts here as we close out today's lecture, since we're about an hour 15 now. There's this quote that I kind of thought was apropos for my thoughts on defining intelligence, that there's this U.S. Justice of the Supreme Court, Potter Stewart, and he said, "I could never succeed in intelligibly doing so, but I know it when I see it." And so this is my kind of how I view, or a lot of people view, how do you know when something's intelligent? Well, I can't really pin down what it is that makes it intelligent, but when I see it, I'll know it. I'll know when that's intelligent. Now, he wasn't talking about artificial intelligence or intelligence. He was actually talking about obscenity in 1964. But it turns out that defining intelligence is very similar to that. It's like you look at that thing and you could say, well, that's not intelligent. That's just a machine doing a dumb thing, like an elevator. That's not intelligent. Sure, it takes an action and it serves your needs, but it's just a stupid machine doing a stupid thing. But it might turn out that defining intelligence can be more difficult than even his, at least Potter Stewart's version of defining obscenity, is that we might have something that looks intelligent and behaves like we do or tricks us. But how do we know that that's really intelligent? For example, like a large language model. A lot of people will talk to a large language model. They'll ask it complex questions. It'll give complex answers. They'll even seem to think it has a personality. It'll compliment them. It'll become like their friend. It seems like an intelligence, but and next semester we're going to learn how these work. Once you start digging in and learning how they work, it's almost like the illusion gets shattered and you're like, well, how could it be intelligent? How can it really have thoughts at all when you understand how it works? Now, I do have a argument for, I could say the same thing about humans. Like, how could they be intelligent if you understand how they work? But we'll save that for a later lecture, since we've been talking for a while now. Now, my final thoughts here on studying AI is AI. We talked about it being dangerous at the beginning with the Terminator. And so, like any technology, it does have dangers. And like every other existing technology, that once the genie's out of the bottle, it's out. And with that promise of power comes danger, and with danger comes responsibility. And so part of the issue and part of the why we're studying it is precisely because of this. And so my final thoughts on why we're studying it is understanding the nuts and bolts of it, and other technologies is going to help us. And it's going to help us understand AI systems, but not just that. It's going to help us with a lot of other things as well. In other words, information theory, language, and patterns, that feeds into a lot of things besides just AI and machine learning. So here's what I hope you get from this class. I hope you get kind of this joy of enlightenment of learning this stuff, this power of understanding over the material that we're going to cover. In other words, I want you to learn something that's going to give you capabilities for doing things. And at the end of the day, though, like you might say, well, why understand? Why is it important to understand this? Why would I want to? And I want you to develop skills so that you, especially a lot of people are like saying, oh, computer science is going to go away as a discipline because AI is going to replace all the programmers. I don't, while it can replace certain low level kinds of development, I believe that that's overblown. And we're going to see later on in the course sequence where AI with large language models can fail miserably at things that are not complicated to understand. But at the end of the day, AI can be great at supercharging our capabilities and making us better computer scientists or better developers. And we need to understand so we can develop skills to be better than AI. In other words, do better than it can do. And also, since AI, especially large language models, are trained on a large volume of data, they can only really put together what it is they've been trained on. So they're not great at innovating. They're better at just recycling things that have already been fed into them. And so I want you to become more of an innovator, not just a user, somebody who can think about these things and understand them so you can then apply them to intelligently to new things. I want you to be able to learn to when and why you should trust or when and why you should distrust AI. I want you to be able to lead and not follow. In other words, adapt and evolve. And the only way to do that is to truly understand what it is we're doing. And at the end of the day, learning why and how things work is just itself very satisfying and very powerful to know that. And I want you to understand that AI is this kind of tool that we can understand. It's not this magic thing that thinks. It's not this magic mystical wizard that you talk to and it just gives you things. I want you to understand kind of at this much lower level how it works and what's going on inside of there, because that is going to give you power. And then at the end of the day, if you have that excitement and that understanding, I want you to be able to pass that on to other people and teach other people, because this stuff is going to be important. Just like there are a lot of things that have transformed our society, like the invention of the internal combustion engine, the invention of electric lights, the invention of refrigeration, the invention of even going back the plow. All of those inventions have completely transformed society. AI is the internet as another one. AI is one of those things, and especially where we are now, it's poised to transform society. And so if you're not somebody who understands it and can use that and be part of innovating with that, then you're going to be more likely to be left behind. And so I want you to be able to learn and understand this stuff because it's fun, because it's really cool, and because it's powerful, and because it's going to be necessary in the future. Now, also understanding a technology is the best way to control it rather than having it control you. It's the best way to get power over it. And so at the end of the day, I want you guys to have that understanding, that deep and broad understanding of this material, or at least get you started down that path, so that when the robots do rise, when the AI does turn evil, there'll be at least some of us that understand well enough to uh, stop the AI, or at least have a chance at it. And this sounds pretty dystopian, and I meant this to be humorous more than anything else. But our skills may be needed in the future, when the AI decides uh, that it's had enough of us. That we might need to understand how it works, so that we can. Well, we might also need to understand how it works to know how to make AI that is safe and understandable, and know what not to do with it, and when to trust it and when not to. And that could be something like obviously dramatic, like a Terminator robot, that and Skynet that decides to do away with humanity. It could be something as simple as just trusting something that it told you, and taking it at face value. With once you understand how it works, maybe you won't do that as much. So the big thing, though, is I would like you to tell me what you want from this class. So if you would like to spend a little bit of time going to uh, the forum, maybe answer uh, that question, maybe interact a little bit with each other, talk to each other about that. What do you guys want from this class? What do you want to learn from this class? I do think we're going to have a lot of fun. We're going to make some code. We're going to write some things. And at the end of the class, we're going to have a chat bot that we can teach things to. It's going to learn from us. And not only that, you're going to be able to understand 100% of how it works and see 100% of the code that's in it. I promise no black boxes in that. We're not going to just download a thing and then use it and have it do a thing for us. You're going to understand all of it, from the bottom all the way up, and be able to understand how it works. That might take a little bit of the magic out of it, but it also, for me, I think it adds a lot of magic to it, because once you see how the sausage is made and you see how it works, now you know, gives you ideas for how you can make changes to it and make it better, or do things within the future. All right, we will stop there. And so this went on a little bit longer today than I intended, but I appreciate the patience. Next class, we're going to start digging in a little bit further into thinking about artificial intelligence, and then shortly after that, we're going to get into some actual programming stuff and some material, and start actually rolling our sleeves up, getting our hands dirty, and doing some stuff. I promise we're going to get there. We'll get there pretty quickly. So I will stop there. And if you have any questions or comments, feel free to reach out on the forum, or via email, or via text message. And I look forward to seeing you next time. Thanks.